next video. All right, so one more thing before we continue on with our lesson. We were just talking about Charles's law, okay? One thing that you need to notice is on this scale, there's these little dots right here, okay? And this is just a dumbed down version of the one that's in your book. You need to know what that means. Those dots there are actually showing that we don't have data for those points, but that we're predicting that that's how it would go. So this idea is called extrapolation, okay? And you do this all the time, you probably just don't realize it. So the whole idea behind extrapolation is you are getting a trend from your data. Let's say you have a bunch of data points, okay? And it's following a specific trend, okay? A lot of data. And then for some reason, you just can't get the rest. There's a little bit of a gap. If it follows a trend and it's just a little bit that you're missing, you can extrapolate the data, which means you just continue the trend even though there's no data for that region. So if you take a look, all these data points we have, except for like the very little bit. So we're assuming that if we were to measure it, because at a certain point that volume gets really, really small and it's really hard to measure that gas. So we're assuming that it's going to continue to follow the trend that it has. Now, really quickly, you have to be careful. When you are extrapolating data, the basic rule as a scientist is you need to have a lot of data and just a little bit of extrapolation, okay? So that means you can't just say, oh, I'm missing some, I can just apply this to everything. You can't do that, okay? So something like, I think in the book they talk about Darwin. He took a little bit of data with the finches and their beaks changing a little bit over time to suit the needs of the environment with food. And he said, okay, well, I have data here and I see that this is changing. Therefore, I'm going to assume that if they can do it here, they can also go ahead and just change from one species to another. That is a poor use of extrapolation, okay? You need to have a lot of data, a little bit of missing data in order to do that correctly, okay? So let's go ahead and move forward. We talked about Robert Boyle and we talked about Charles' law. Now, if we put Boyle's law and Charles' law together, okay, this is what we're concerned about. That's going to give us the combined gas law, okay? So instead of just putting this portion or the other portion, we're going to smush them both together and use that. So you don't need to memorize either of these two laws, but you do need to know what the combined gas law is, okay? So we've got pressure, volume, and temperature. And if you remember, the first one, we had pressure and volume, and the temperature remained the same. Remember that? And then the next one we talked about, the pressure stayed the same, and we had volume and temperature. Okay? So really, we're just taking both those laws and smushing them together, and this is what you get. Okay? So this is the equation we are going to use when we're talking about pressure, temperature, and volume. Okay? So when we're using any equation in this module, you need to remember that we're always using the Kelvin scale, because think about this. We need to have it to not be able to touch zero. Because what if we had a zero right here? We know what happens when we divide by zero. Okay? You can't do this. Okay? So we're not going to get a real number. So in order to avoid that, the chance of getting zero, we use the Kelvin scale because you can never reach zero. Okay? You'll never be able to reach zero down there with the temperature. Okay? So let's look at the first examples. These are pretty easy. We're just going to be plugging numbers in. Okay? It says a weather balloon is filled with helium before it is launched. On the ground, the gas has a temperature of 25 degrees Celsius and a pressure of 1 atmosphere. The volume of the balloon is 4.5 meters cubed. As the balloon rises, however, the pressure and temperature change to 0.30 atmosphere and 15 degrees Celsius. What is the new volume of the balloon? Okay, so when you're doing these problems, we're going to identify all the numbers they give us. We're going to identify if it's a volume or a temperature. And then they say, and then it changes to, that's going to be where you get your number 2. This is the second version, you could say. Okay, so the first one, let's just go ahead, P1, V1, T1, P2, V2, T2, okay? We're just gonna list them all off like this, and then we're gonna see which one we need to find. They said, what is the new volume of the balloon? Ding, 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 that's what we're looking for, okay? So let's plug in all of our numbers. The gas has a temperature of 25 degrees Celsius, so that would normally go here. But keep in mind, we can't use that. We need to use the Kelvin scale. So in order to do that, we have to add 273.15 to it. Oops, let me move this down just a bit. What did I say? 25? Okay. Oops. So when we add that, we are going to end up with 298 Kelvin, because remember, we can only go up to the first with the significant figures. So there's our new temp, 298. So keep in mind, always watch out. They're probably going to give it to you in Celsius to make you do that extra step. It's got to be in Kelvin. All right, so the new pressure is 1 atmosphere. I mean the old pressure. And the volume is 4.5 meters cubed. And then it says the balloon rises, and the new pressure is going to be 0.30 atmosphere and 15 degrees Celsius. So I'm just going to go ahead and add that again. When I do that, I get 288. Okay, so now I'm ready to just go ahead and plug everything in. I need to solve for volume. So I'm going to use algebra and move things around, okay? So I'm going to do that, and this cancels. If I divide by that, this cancels, and I'm left with this. So really, I just have to plug these things in, okay? So let me do it over to this side so I have enough space. So I'm just gonna plug each thing in. I've got 288 Kelvin times 1 atmosphere and 4.5 meters cubed. That's on the top. On the bottom, I've got 0.30 atmosphere and temp 1, 298 Kelvin. So go ahead and look at your units. Your Kelvins cancel, your atmospheres cancel, which is good because you need a volume, and that's your volume unit. So if you crunch through all of this, you're going to end up with 14 and that unit, meters cubed, for that new volume of the gas in the balloon. Okay? So really, it's just identifying what numbers you have, which one you're looking for, making sure all of your units are correct, and just plugging them in. Okay, so let's try another one. All right, the next one says, a gas is stored in a 3-liter container at a pressure of 456 torr. If the temperature stays constant, what will the pressure of the gas be if the volume is decreased? So once again, I'm gonna go ahead and just put my equation up here so I know where to start. I'm dealing with these 3 things. And now listen to this. This helps you out. It says if temperature stays constant. So we don't have to deal with temperature at all. So I'm just going to go ahead and cross it out. Okay? So really, now my equation is just this. So it's nice when they say pressure doesn't matter or temperature stays constant, something like that. You can just get rid of it. So now I'm just going to go ahead and list P1, V1, P2, V2. And they said, what will the pressure of the gas be? So I'm looking for the new pressure. So I'll plug my things in. 3 liter, so that's a volume of gas at a pressure of 456 torr. And it says the pressure of the gas, the new volume is 0.75 liters. Okay, so I'm solving for P2, so I need to get that V to the other side. Okay, so I'm just going to plug numbers in. So I've got 456 torr times 3.00 liters, and then on the bottom I've got 0.75 liters. So my liters is going to cancel, and my pressure is going to be torr, which is good. That's a pressure unit. So if I crunch all this out, I'm going to end up with 1.8 times 10 to the 3rd torr. So that's the pressure, okay? So go ahead and do the on your owns, 1, 2, and 3. They're gonna be just like this. You're gonna be using your new formulas, plugging those in, and seeing what you come up with, okay? All right, so the next thing we're gonna talk about, now that you've gotten a little bit of practice from that, is we're gonna talk about properties of an ideal gas, okay? So we've used the combined gas law, but it turns out that there are sometimes you can use it and sometimes you can't use it, okay? In order to be able to use this useful law, you have to have a gas at an ideal condition, okay? And I'm gonna go ahead and stick this up here, okay? Properties of an ideal gas, okay? So, properties, a gas is an ideal gas if there's 3 things that it has to be. Molecules and atoms of a gas. So be thinking all those little particles bouncing around, okay? When they're bouncing around, the molecules or atoms of gas are small compared to the total volume, okay? So the amount of those atoms or molecules is pretty small compared to the total volume of that area. Second, they have to be far enough apart so there's no attraction or repulsion, okay? So as they're zooming around, they can't be so close that they're actually being affected by any pull of attraction. And 3, they can't lose energy colliding either with each other or the walls of the container. So think about that. As they're bouncing off each other, as they're colliding with each other, or they're bouncing off the edge, they can't lose energy doing that, okay? So these are the 3 things that you need to have an ideal gas. I think this is called that they have elasticity. I think that's the word that they use. And also, we would say that, well, how do we know these things? That seems like an awful lot to know. But there's a way that we can know these things. It turns out that if a gas has a temperature of 273 Kelvin or higher, and has a pressure of 1 atmosphere, that's the atmosphere around us, or lower. So we're thinking higher temperature, lower pressure. These gases are ideal. And when they're ideal, we can work with it. So in this course, it's a little bit more advanced working with non-ideal gases, so we're not going to be working with them. You don't have to worry about that, okay? So for our uses in this module, you're going to be able to use our gas laws for everything. They're going to be ideal gases. But they do want you to know what makes something an ideal gas, okay? So we call it standard temperature and pressure, STP. Okay, so if they ask you what is the STP? You would say the temperature should be 273 Kelvin and 1 atmosphere for pressure. Okay, so that's what's considered standard. But when you need to know if they give you a temperature and a pressure and they ask, is this gas ideal? You need to remind yourself it has to be either 275 or higher for temperature, warm temperature, low pressure, 1 atmosphere or lower. It can be lower than that, less than 1. Okay, so that's what we would consider ideal. Okay, let's see, where are we at? I'm going to go ahead and stop there since we talked about those gas laws. We're going to take this idea here with what an ideal gas is, and we're going to talk about how that relates to Dalton's law of partial pressure. Okay, so we just talked about ideal gases, what they are, what they need to be.